So let us continue then. A word of warning before we start. This part is more experimental in some sense. So whenever you read something with like theorem, lemma, you just really understand this up to very carefully checking. We might delay a lot the lecture step. So and all mistakes are on my own, not on the authors. Okay, another disclaimer that's very important. But I mean, it's gonna work. There, we have to write, right? This is the lecture number 9 on this. So I'm like, yeah, there's a full story I didn't tell you. In the meantime, we're never gonna finish anything. But in October last year, I said it will be 1 more week. Here we are. So let's see how. I mean, it's really long thing, right? So well, okay. So with this point of warning, words of warning, let's see what we can do. What's the spirit? I mean, I'm sure that if you have attended like since talks in the last 5 years, you're gonna recognize many of these results. Some of them appear in some shape in this Katzarkov Kontsevich in you. What you're gonna try here to disguise in a new quote and get some examples, new examples of applications. So before we just had this A model manifold, now what we're gonna do is to actually very quickly look to A model bundle because we want to understand the quantum differential equation very heuristically, and let's try to not get lost in some technicalities that are many and require a lot of work. So our idea is to then look to the A model and bundle, but actually not exactly to them as a full, but to the quantum differential equation, and look to certain solutions, but sections, and growth somehow of these sections, and see how they connect with the questions in directional geometry. Right? So this is the program. Again, be a bit like a patient because whenever you read like theorem, lemma, it means work in progress lemma, work in progress theorem. So let's see how it goes. Excursion number 3, the arithmetic of dimensions. Okay. So what is the setup? We have built this A model manifold so far. Now, from Tony's talk, there is this natural A model F bundle. Do this by looking to this germ of analytic disk. So then you have this du here to me is keeping track of non-computative structures and the parameter spaces vary. This non-computative structures in analytically forgetting all these confusions, these difficult parts that Tony was explaining to us. And the important thing to us is not actually the bundle itself, but the connection on this du direction. So we're going to be interested on this guy here. This is the grading operators, grading that appeared on the stock. They don't depend on vectors, the deformation parameters. We have this other vector field. And to us, quantum differential equation means solutions of this equation. Okay. So what we're going to try to connect here, or to explain, elucidate, convince, is that looking to solutions of this equation can lead to new answers in variational geometry. So here, like forget a bit the equivalent setting and just really focus on this. Again, this is very experimental in many sense. So, down. So as before, case or like a non-Euclidean field. And let's put this definition here, what it means. So we want to understand solutions to this equation when this parameter u is actually like reduced to 0. And because of this, let's put a formal definition somehow over this field here. Let's write it together. We're going to call a formal solution in the direction of a generalized eigenspace. So as before, you have your E model manifold. There's something I would like to mention to you that whenever you have your A model manifold, and you have A model of bundle, right? And so this now is a bundle over Bx and over the Bs. But when you restrict the parameter u equals to 0, and you look to the fiber of your bundle at the points P and u equals to 0, this coincides with your tangent space of your bundle. So it means that residual information on your A model are actually the tangent space of your A model. And once you have extended your connection, u equals to 0, for instance, if you put u squared here instead, you evaluated u equals to 0, you gain your quadratic vector field multiplication. So then remember, whenever you have here a point P and a coordinate u, you can look at the fiber. If you set u equals to 0, you get that this fiber is isomorphic to the fiber of your model. Now we just choose this connection on this u direction, have the quantum differential equation that you are looking to solutions for this. Now, because you have your parameter space, you have your operator quantum differential equation, they vary with the points on your modeling. We convention this definition here. We're going to say that a formal solution in the direction of a generalized space, because again, the quantum differential equation has this component of the order vector field, is a guy expressed like that. So let's see, u, some power us, some log, all sitting in an element, this huge guy. This is the fiber at your bottom. So we're gonna try to guess solutions for your quantum differential equation, departing from an ansatz like that. And it means that in the direction of this generalizing space, because now the exponential term here, it will be of this form. We have like also a rational number here, called this formal exponent. And this is the idea. Let's try to look to sort of like solutions coming to this quantum differential equation by ansatzes like that. Sounds a bit unmotivated if you think about it, but the idea and the expectation is that from this S guy here, we're going to start some negative number, such that after you multiply by 2, you get a positive number. And the idea is that this number corresponds to the action of the Serre functor on the piece in the semi-orthogonal decomposition that's expected to correspond to atoms. I mean, those are the vectors that I'm like jumping to get to the 9th vector here. So, but the story is there's expectation that the atomic decomposition is correspond to a given like preferable semi-orthogonal decomposition in the category of derived coherent sheaves. Jeremy's talk is very much related to that. And when you have species, you have this dimension of notion of a dimension for like species. And the idea is that from the point of view of a model, this S here up to multiplication by -2 will reflect the dimension of this. Yes, Paul?
Only M are going to tell us.
Yeah, I mean, I wish no one had asked this, but this didn't. So you see, when you are in this model story, you have your think about the first part where you have like this Q belonging to the complex number. It would be okay if you set it to 0, right? Now you just reduce to a standard multiplication. So you get meaning the one multiplication will go to Pascal product, and this M here it appears in the ansatz when you are in this limit when you take Q. So plus it has to do with the importance of multiplication, but
In some Jordan block size.
yes, exactly, yeah, exactly this. But let's not get into this, please. Yeah, but indeed, so you're in face of this as you are proposing some sort of like ansatz to solve your quantum differential equation. This M here appears when you want to set this Q equal to 0. But because you are in the same model story here, actually we're gonna assume that in our proposed solutions M is equal to 0 because we are in this tube domain that the coordinates, the non-local coordinates are actually have valuation greater than 0, so we'll not get much upset about this. But we want to look to this equation. And my claim is that in these lectures, between the one that I just gave, I've lost many others until this lecture is in the written text, is that this has some deep motivation coming from the notion of dimension of category. That's encoded on this guy. So what you're gonna do is the following. Pick some lambda at a point P. Of course, here, I mean, Bx raw. I'm sorry, I have to call it the fixed locus. Like, let's speak like a even generic. My point is the definition doesn't depend on this that you are in the fixed locus, but to try to remember, keep track of propriety, it's okay. But this definition we can make everywhere, right? So you pick a lambda that's like lies on the spectrum of the multiplication by the order of some point when you are in model manifold. And now we're going to consider all the space of all formal that are called HLT, all this is on such solutions in the direction of this generalized space. So again, you pick an eigenvalue lambda, depends on the parameter B. Then you have your ansatz. This is where lambda is appearing. You collect all of these guys, possible guys, that solves this equation. Then you define what is the name. The spectral dimension is what? It's -2. Then you look to the minimum of these numbers appearing here, where this S is this leading point. So you see, you propose like an ansatz, then you look in the direction of that corresponding eigenvalue. You extract this number S, just like here. So you see, you propose the ansatz. Actually, we are always going to assume that the m is to 0. So you have this ansatz, the corresponding lambda. You may have like many solutions to like these enhancement S guys that appear here. And then you look to the minimum of them, and -2, this minimum. You call this to be the spectral dimension of this generalized space. And that's what it's going to be stated on these lectures in the appropriate chapter. Is expected to correspond to the dimension of a category appearing SOV that you expect to correspond to atomic decomposition. So this is a way to put this categorical picture on the level of a model. This is the story that we are going to tell. Let's see an example. So you pick X to be your smooth cubic threefold, right? So then you do the array model. Now you have this Q parameters, not called parameters. You have the matrices, but let's look to this operator only acting on the ambient homology for the Q. And then you have to look for formal solutions. So expressions like that. Remember, I said like, forget this M, we're not going to care about this. We're going to propose an ansatz like that as solution. And then it turns out that when you plug into equation, you're going to get like some recurrence relation. And if you compute the small quantum multiplication for the cubic threefold, you get 3 eigenvalues. One of them is 0. And then all that I'm saying is that here, in the corresponding eigenspace for the 0, in this representation for the 0, we're going to get 2 exponents, because then we're going to have like 2 solutions. One with -1/6, and the other with -5/6. I mean, believe me, it's possible to do this computation, and if you can check, and it's really you can check, because you know even the description of a small quantum homology in this case. So you can actually check it, that you get this number. So just by this is corresponding to the eigenspace at 0, or the ambient, or the action of these guys in the ambient part of the curve. And then you compute the dimension, right? So then you get 5 terms.
Wait, sorry. Aren't we allowed to move in the Frobenius? Like the given tall computation?
It's for the small part, right? Yes. Yeah. I mean, there's a bit of a fly here. Indeed, I'm doing the computation in the small quantum multiplication here, getting the number, and saying that when you do this A model, we start. Yeah. So here, precisely, I'm corresponding here the A model manifold, the point where you set all the other coordinates to 0. You're just like really on the non-conf parameters. So it's actually the non-Archimedean story for given values. You are on the part of your A model manifold only given by this domain on the torus. So indeed, I'm setting all order coordinates to 0. Because in the definition, I don't require that I'm in a point of like locus. I mean, the definition I can put on every point of your A model manifold. This I'm doing for the same case as given. So look to the A model manifold, set out coordinates that are not up to 0, to compute the action. Then in this case, the order vector field will reduce to fraction class multiplication, as we have argued in the first class. So it's just fraction class multiplication. Look to the action of this guy in the ambient homology. You're going to get 3 eigenvalues. Now this is corresponding to the eigenvalue at 0. So indeed, that's the computation we are doing. All right. And then you can check that, okay, this dimension in this case is 5. Now there is this story about, so I guess it wasn't so. The first one here, I might be wrong. Semi-orthogonal decomposition for the cube threefold. And then there is the self-component and 2 exceptional objects. Then this notion of dimension that I said, do the self-component, is precisely 5/3. So that's what this is mirroring here. Like a model manifest. Like the notion of dimension appearing in the semi-orthogonal decomposition of the Dirac category. This is the idea.
So is it Serre dimension or?
Yeah, Serre dimension, precisely this, Serre dimension. So
there's an upper and lower one though? Is there an upper and lower?
Yeah, exactly. I mean, so indeed, for the business, I'm sure that so this is fraction of right? And then it's 5/30, and that's
in this case.
Yeah, in this case, yes. But indeed, you have like if you have many, and it's precisely this Serre dimension, and so that's why I said that it resembles some stuff that happened like on this paper of Katzarkov Kontsevich and M, because then how do they recover the proof of a three-dimensional cubic is non-rational? They compute the small quantum multiplication on the ambient part by using the dental. It's more or less what we're doing here, right? And then they look to the action of the Serre functor on that app. And then they're going to check that it acts as it should not act on curves. That's how they get it. But I'm claiming that this is being manifested by this dimension. Indeed, so it's precisely this. So,
but is there an upper and lower version of your dimension or just one?
No, in this case, we really want only one dimension.
But then it can't correspond in general.
Exactly. I mean, we're mostly, indeed, this is one of the main problems that we face. Indeed. Here, we actually going to stick to complete intersections that have this in general, and check for these cases that we can actually get what is expected.
But even for those, the Serre dimensions are different on a future extension.
That's true. But let me get you some far.
Okay, sure. Sorry.
No, don't worry. It's good. It's important. But I also, indeed, this is very important. What you said. So let's try to keep this. I'm going to propose some forms. And so the conjecture can be made precise, but I really didn't want to go to this category theory in general.
Sure.
But let's see some formulas, some precise formulas. We're going to propose some formulas. But indeed, so you see what you're doing here. We have like your A model manifold, then you have like a bundle, you have connection to the direction, plus differential equation. You want to look to this sort of like numbers. And then you have like the solutions that we propose depend on the generalizing space that we're pursuing. So here in this case, because you have like so you have like 5/3, this is the dimension of this corresponding eigenspace. So for Kuznetsov, there are like semi-orthogonal decomposition for this cube. You have like this Kuznetsov component that has this dimension, and then 2 exceptional guys that if you compute here, you're gonna see that the corresponding dimension spectrum for the other 2 eigenvalues is 0. Okay, 0. Now what you're gonna do? We know that you have like this K analytic space, and we want to see this as some parameter. We want to define some function on this. This is the function that will count the number of distinct eigenvalues for this multiplication. Now remember, in quotations, lemma right? This function is lower semi-continuous with respect to the topology. In particular, we can show that we can do some partition of this Bx space here in strata by the corresponding assignments of the number of eigenvalues on this box. And then you use the fact that you can work out the choice spare space and so everything's okay. Actually, there is like a dense open principal stratum where the number of eigenvalues is not. Okay. This is what the number of these distinct eigenvalues is not. Because we are doing this sort of collections, you have to do this because these atoms, like the generalizing in spaces, they depend on the points on the parameter space that you are. So you really want to keep track of them. And also you must remember that, as Maxi said, the atoms they want to keep like splitting. So I mean, you have to make a notion that of this spectral dimension that will depend on the point where you are moving. But to do this more or less coherently, you have to prove some like analytic properties for the quantities here involved. Now we define what? So we fix the principal stratum. So that says like a distinct eigenvalues. Then we're going to define this spectral mood set. To each point B, you're going to associate the mood set of the spectral dimensions. Okay. This is going to be like symmetrical, like numbers in Q. And in quotation again, lemma. There's a function, right, that's going to associate to these points. The symmetric guys, it's upper semi-continuous. It's right. But I think it's part of it's totally okay. So in particular, again, by pair category theorem, there's going to exist a generically mood set that will be constant over this dense open set with crystals. Okay. Now, when you have this closed subspace, right? It's also it shows bare space. It has its own principal stratum itself. It's closed there. So then you can define what the generically mood set for this guy. Now we take out the paragraph and just put like straight B hot. And you define the corresponding mu. I mean, sorry, there's a typo here. No, sorry, this is actually why. The maximum of these guys in the mood set. Why I'm saying maximum? Because you can put the lexicographic order here on this collection of mood sets. See? Now we define the maximum on these guys in the mood set in lexicographic order of the generic dimension of an atom on the Hodge locus of a variety one. That's the point. So we're going to try to keep track of this spectrum as long as you move on your parameter space, dimensional spectrum. Lemma, this is hard. This is the hardest part. For any complex smooth projective variety, you show that this number is bounded by its dimension. They're bounded by its dimension. Functionality criteria. If X is a complex smooth projective variety of dimension greater than 2, suppose the maximal generic spectral dimension of the Hodge locus satisfies this. The variety is normal. Okay. This is the point. So, if you then by doing log formula and then showing compatibility, now you have to use U, Jang and Jang to prove the decomposition of returning goes to F bundles on Archimedean setting. Then knowing this log formula and this fundamental lemma, we can actually work out this result by weak factorization. So this is pretty. What you're gonna do in the remaining is to actually see this criteria in action in some examples. But this is the trick. It's my opinion. So let's check for this cubic threefold. So it has dimension 3, of course. Then this threshold appearing in the theorem the same as 2 is 1, right? But we just have computed this dimension, 5/3. How this number is like bounded by below by 5/3. That's greater than 1. That's not right. Okay. Another example. So general formula nonsense here. So if you pick a funnel complete intersection of R hypersurface of corresponding degrees, then you just find the sum, the max, and the funnel index. Then actually, in this setup, you can check that there's zero as eigenvalue, right? And then when you compute the corresponding dimension of the spectrum, this is given by this formula. It's the dimension of the variety minus 2 times the funnel index divided by the maximum of these guys up here. The general formula. Let's see an application now that is you pick quantity for fold, funnel index 2. You just plug in the formula. This is 3. 4-fold, 4 minus 2 is 2. Because 3 is greater than 2, it's no ratio. It's even. You start to operate in many miracles, like this out of arithmetic. Another example, 24-fold. Funnel index 1. Spectral dimension 3.6. 4 minus 2 is 2. No ratio. Now, the product of a two-party, product of a two-party tripoles, you get like 5/2 plus 5/2, that's 5. 6 minus 2 is 4. No ratio. Quintic threefold the same. But now we lack here. If you try to multiply the cubic with P1, inconclusive the result. So there is some reason, of course, do not prove everything, right? There's no constraints. Sorry? Maybe I did something wrong here, like a
threefold, maybe fourfold.
yeah, fourfold. Sorry. I mean, it was indeed. I was considering. Sorry. Yeah. Sorry. I mean, it's 3 a.m. Sorry. Sorry. Very sorry. Fourfold. Yes. But in some cases, you're still not able to get it. Also, it's very tricky in some cases that are very interested. So, if you pick discussion with high variety, we don't have like a formal proof for the corresponding formula, but we have a this. Mean. We expect that it could be proven that should be precisely this. The dimension minus the index. Whenever we have like this intersection of gas minus. And in this case, if you do this for discussion with the intersection of the 5, then you get 2. The dimension 3 minus 1. 3 minus 2 has that. The 1 is so non-rational, but the fourfold we cannot do. Awesome. And then this is the story, and just because I promised it to so yesterday, there is a formula for complete intersection. I mean, I just put question marks because it's checked, but it should be like this. It's correct, right? It's correct, right? Yeah. So this is the formula for complete intersections. And with that, I finish my serial talks. Thank you so much. Thank you.